December 19th. Lantiling Arsu. Mark it quietly, clearly, because on that day, you witness something only a handful of human generations have ever seen: an object from beyond our solar system passing within striking distance of Earth. 3i. Atlas is screaming toward us right now at 7. 0, 0, 0 miles an hour. And it's unlike anything we've ever tracked. It's accelerating when it shouldn't. Outgassing materials that refuse to fit our models. And in exactly 27 days, it crosses Earth's orbital path at a distance closer than the Moon. NASA's watching. ESA's watching. Every major observatory on the planet has telescopes locked on this cosmic intruder. But here's what the headlines keep glossing over: the physics of this object doesn't add up. You're about to get the unfiltered scientific breakdown of what December 19th really means: the orbital mechanics, the collision probability, the detection systems that almost missed it, and the brutal truth about whether we could stop something like this if we had to. Before we go further, if you want to understand space events without the panic or the fluff, subscribe and hit notifications. We translate the universe's chaos into clarity. Take a slow breath as we go, and let the equations do the heavy lifting, because even the strangest sky story feels quieter when it's measured, mapped, and spoken in plain language. No hype, just calm, careful truth. And if you're already intrigued by what's coming, that like button helps more people find real science. Let's get into it. Let's rewind to October 13th. Lantiling Arshasa. That's when astronomers first spotted it, a faint smudge of light moving through the constellation Serpents. At first glance, 3i, Atlas looked like just another comet. Except it wasn't. Within 48 hours of tracking its path, something became disturbingly clear. This object wasn't born here. Its trajectory told a story that made astronomers everywhere stop what they were doing. The numbers didn't lie. This thing was moving at 31 kilometers per second, relative to the sun. Far too fast to be bound by our solar system's gravity. It was a visitor from interstellar space, and only the third one we've ever confirmed in the entire history of human observation. Think about that for a second. Humans have been watching the skies for thousands of years. We've cataloged millions of asteroids, comets, and space rocks. But interstellar objects, we've confirmed exactly 3. The first was Oumuamua in 2017. That cigar-shaped mystery that baffled scientists when it accelerated without any visible propulsion. The second was 2i, Borisov, in 2019. A more normal comet that at least behaved the way our models predicted. And now 3i, Atlas. But here's where it gets unsettling. This one doesn't fit either category. Dr. David Finoya from NASA's Jet Propulsion Laboratory said it best when the preliminary data came in. We're seeing outgassing activity consistent with the comet, but the acceleration profile is off by a factor we can't explain yet. Translation, it's spewing gas and dust like a comet should when the sun heats it up. But the way it's speeding up doesn't match the gas jets we're observing. Something else is pushing it, and we don't know what. Let's talk about what makes an interstellar object so fundamentally different from everything else out there. Every asteroid, every comet, every grain of dust you've ever heard about in our solar system is trapped here, bound by the sun's gravity in elliptical orbits that bring them back around, sometimes over millions of years. But interstellar objects, they're on hyperbolic trajectories. Picture a curve that swoops in toward the sun, whips around it, and shoots back out into the galaxy, never to return. That's 3i, Atlas. It came from somewhere out there, beyond the reach of our sun's gravitational influence. Traveled through the freezing void of interstellar space for who knows how long, and is now cutting through our cosmic neighborhood on a one-way trip. The math is staggering. To achieve the velocity 3i, Atlas is carrying, it had to be ejected from its home star system with violent force. Probably during the chaotic early formation of planets, when gravitational interactions were slinging objects around like cosmic billiard balls. Imagine it being a chunk of ice and rock, minding your own business in orbit around some distant star, and then getting kicked out into the darkness at tens of thousands of miles an hour. That's this object's origin story, and it's been wandering the galaxy ever since, until gravity from our sun bent its path just enough to bring it screaming through our solar system. Here's what really gets scientists excited and a little unnerved. We can calculate 3i, Atlas's orbit, with absurd precision, using data from observatories like the Asteroid Terrestrial Impact Last Alert System. Yes, that's what Atlas stands for. Astronomers have mapped out its exact path, and the numbers are wild. On December 19th, Lianqianling Ashu, it crosses Earth's orbital plane at a distance of approximately 0. Lingarchi, Devon 27 astronomical units. That's roughly 5 million miles. Now, before you breathe a sigh of relief, let me put that in perspective. The moon is about 23900 miles away. So, yeah, 3i. Atlas is passing us at a distance, about 10 times farther than the moon. But in cosmic terms, that's a whisper. That's threading a needle. NASA classifies any object passing within 0505 AU as a close approach. This thing is coming in at about half that distance. And here's the kicker, we almost didn't see it coming. The Atlas survey system is specifically designed to catch near-Earth objects. But 3i, Atlas was spotted relatively late because of where it came from. It approached from the direction of the sun, meaning for weeks it was hidden in the solar glare. Invisible to ground-based telescopes. By the time it moved into a position where we could track it properly, it was already well inside the solar system. If it had been on a collision course, we would have had maybe 3 months of warning. 3 months to detect, confirm, calculate, and respond to an interstellar object barreling toward Earth at 7. Home MFA. Let's compare this to our previous interstellar visitors for a moment. Oumuamua was detected after it had already made its closest approach to the sun. We literally caught it on the way out. By the time scientists realized what it was, the window to study it was closing fast. It's now over 5 billion miles away and accelerating forever beyond our reach. Dve Boriso gave us more time. We tracked it for months, captured detailed images, analyzed its composition, and confirmed it was a comet from another star system based on its chemical signature. Specifically, an unusually high concentration of carbon monoxide that doesn't match anything formed in our solar system. But 3i, Atlas, it's giving us the best observation window yet. And what we're seeing is deeply strange. Spectroscopic analysis, basically breaking down the light, reflecting off the object, to see what chemicals are present shows. 3.1. Atlas is releasing water vapor, carbon dioxide and carbon monoxide as it heats up. Totally normal for a comet. But the rate of outgassing doesn't match the acceleration we're measuring. According to the laws of physics, when a comet releases gas, those jets act like tiny rocket engines, pushing it slightly off course. We can calculate exactly how much push those jets should produce as. And for 3i, Atlas, the math doesn't add up. It's accelerating roughly 15% faster than outgassing alone can explain. Sound familiar? It should. That's almost exactly what happened with Oumuamua. Scientists proposed dozens of theories. Maybe it was rotating in a weird way. Maybe it had an unusual shape that amplified the rocket effect. Maybe it was covered in a super reflective coating that let sunlight push it harder. Some researchers, like Harvard's Avi Loeb, even suggested it could be an alien probe using light sails for propulsion. The scientific community mostly rolled their eyes at that one. But the uncomfortable truth remains. We still don't have a fully satisfying explanation for Oumuamua's acceleration. And now 3i, Atlas is doing the same thing. What are the odds that 2 out of 3 confirmed interstellar objects behave in ways that break our models? Either we're fundamentally misunderstanding something about how these objects work, or interstellar space is full of weird stuff we've never encountered before. Either option is unsettling, in that slow, lingering way. So, where exactly did this cosmic wanderer come from? Tracing its path backward through the galaxy is like running a movie in reverse. Astronomers at the European Space Agency have done precisely this, using the object's current velocity and trajectory to calculate where it was millions of years ago. The results point toward a region in the direction of the constellation Aquila. But pinpointing the exact star system is nearly impossible. Space is big, like incomprehensibly big, and even at 31 kilometers per second. 3i. Atlas could have been traveling for tens of millions of years before reaching us. Its parent star could be hundreds of light years away by now, drifting in a completely different part of the galaxy. But here's what we know for sure, and it matters. This object survived the journey. Think about what that means. Interstellar space isn't empty. It's filled with radiation, cosmic rays, and the occasional high-speed particle collision. For 3i, Atlas to still be outgassing. To still have volatile ice intact after potentially millions of years in the freezing void means it's either incredibly well preserved or relatively young in cosmic terms. And that tells us something fascinating about the conditions between the stars. Now, as December 19th approaches, every major observatory on Earth has time booked to watch this thing. The Hubble Space Telescope, the James Webb Space Telescope, the European Southern Observatory's Very Large Telescope. They're all going to be pointed at 3i, Atlas, during closest approach, because opportunities like this don't come around often. We're talking about a once-in-a-generation chance to study an object from another star system up close. The data we gather could rewrite our understanding of how planetary systems form, what gets ejected into interstellar space, and what's really out there in the darkness between stars. But before we get too comfortable with the science, we need to ask the question everyone's thinking. What if it didn't miss? Let's run the nightmare scenario. Forget the 5 million miles of safe distance for a moment. Imagine it, 3i. Atlas's trajectory was off by just a fraction of a degree, a tiny miscalculation in its approach angle. Maybe a gravitational nudge from Jupiter we didn't account for. Suddenly, December 19th isn't a spectacle. It's a catastrophe. What would actually happen if an interstellar object traveling at 0 miles per hour slammed into Earth first? We need to understand what we're dealing with based on brightness measurements and outgassing rates. Astronomers estimate 3i. Atlas is somewhere between 300 to 600 meters in diameter. Let's split the difference and call it roughly 450 meters, about the height of the Empire State Building. Now that might not sound massive compared to, say, the asteroid that wiped out the dinosaurs, which was about 10 kilometers wide. But here's the critical difference. Velocity. The Chicxulub impactor that ended the Cretaceous period hit Earth at approximately 20 kilometers per second. 3i. Atlas is moving at 31 kilometers per second. And in impact physics, velocity matters exponentially more than size. The kinetic energy of an impact is calculated using the formula 1 times mass time velocity squared. That squared part is what kills you. Double the speed and you quadruple the energy. At 3 plus 1 kilometer. S. A 450-meter object carries the kinetic energy equivalent of roughly 500 megatons of TNT. To put that in perspective, the largest nuclear weapon ever detonated, the Soviet Tsar bomba in 1961, was 50 megatons. This impact would be 700 times more powerful. 700 Tsar bombas going off simultaneously in one spot. So, let's walk through what happens hour by hour if 3i Atlas hits Earth. And here's the terrifying part. The location matters enormously. Scenario 1. It hits land. Let's say it comes down somewhere in the central United States. Kansas? Because why not? The moment of impact is almost incomprehensible. The object is vaporized instantly, along with several cubic kilometers of rock and soil. A fireball expands outward at thousands of degrees, incinerating everything within 30 meters in less than a second. The shockwave that follows travels at supersonic speeds, flattening buildings and forests out to 100 miles. Windows shatter across 5 states. The seismic shock registers as a magnitude 7. 5 earthquake felt as far away as New York and Los Angeles. But that's just the first hour. Hour 2 is when things get global. The impact has thrown billions of tons of debris into the atmosphere. Vaporized rock, dust, and ash, all superheated and rising on convection currents. Within 2 hours, this debris cloud begins spreading across the northern hemisphere, blocking sunlight. Temperatures start dropping. Not catastrophically yet, but noticeably. Meanwhile, the shock wave rippling through Earth's crust has triggered secondary earthquakes along fault lines. Yellowstone seismographs are going haywire. Emergency services across the Midwest have collapsed under the sheer scale of devastation. By hour 24, you're seeing the atmospheric effects kick in globally. The debris plume has circled half the planet, and sunlight reaching the surface has decreased by 20%. Agricultural experts are already running models. If this continues for weeks, crop failures are inevitable. Global temperatures have dropped by 3 degrees C. It's December, so the northern hemisphere is already cold. Now it's plunging toward a premature ice age scenario. And we haven't even talked about the fires yet. The thermal radiation from the impact ignited wildfires across a 200-mile radius. Those fires are pumping even more ash and soot into the atmosphere. Compounding the cooling effect. Hour 48. The global economy is in freefall. Supply chains have shattered. Panic buying has emptied grocery stores across 3 continents. Governments are declaring states of emergency. And here's the nightmare within the nightmare, the impact crater. Now, a glowing hellscape roughly 5 meters wide and a mile deep is still radiating heat. Geological surveys confirm what scientists fear. The impact fractured the crust deep enough to expose mantle material. Magma is welling up. What was once farmland in Kansas is now an active volcanic zone that will smolder for decades. Hour 72. The debris cloud has now fully encircled Earth. Sunlight is reduced by 40%. Global temperatures have dropped 8 degrees Celsius in just 3 days. And coastal cities, unexpectedly, are facing a second crisis tsunami waves. Not from the impact itself, but from massive landslides set off by the seismic shockwaves. Entire sections of the continental shelf off the coast of Norway collapse into the ocean, sending long, fast-moving surges across the North Atlantic. The death toll is climbing into the millions. And we're only 3 days in. Now here's the critical question. Would this be an extinction-level event? Probably not for humanity as a species. We're adaptable. We have technology. And frankly, Sandy, 500 megatons, or catastrophic Stilis and Chicxulub level. The dinosaur killer was in the neighborhood of 100 million megatons. Nearly 3,000 times more powerful. But here's what it will be: a civilization-ending event. The global collapse of infrastructure, agriculture, and societal order will take generations to recover from. Dr. Elisabetta Purazzo, who spent her career modeling asteroid impacts at the Planetary Science Institute before her passing, once calculated that an object around 500 meters hitting land would cause regional devastation, with global climate consequences that could linger for years. And that was for a typical asteroid, Tresiguna, Atlas, with its interstellar velocity. Exceeds every model she ever worked with. But wait, what if it hits the ocean? Instead, you'd think water would cushion the blow, right? Wrong. Dead wrong. An ocean impact is, in many ways, worse. When a 450-meter object moving at 31 kilometers per second hits water, it doesn't slow down gently. It punches through the ocean like it's barely there, vaporizing water on contact and creating a cavity that collapses inward, generating a mega tsunami. We're talking waves 300 feet high, radiating outward at 500 miles per hour. Say it hits the Atlantic, right in the middle. Within an hour, waves are screaming toward coastlines on both sides. The eastern seaboard of the United States, the Caribbean, the entire western coast of Europe and Africa, they're all in the impact zone. Major cities like New York, Miami, London. Lagos go under hundreds of feet of water before evacuation is even possible. The human cost is unthinkable. Billions live in coastal zones. The death toll from a mid-Atlantic impact would dwarf anything in recorded history. And the ocean impact comes with a bonus horror: water vapor. The strike vaporizes millions of tons of seawater, injecting it into the stratosphere. That water vapor acts as a greenhouse gas in the short term, creating chaotic weather patterns, megastorms, hurricanes forming in places they've never formed before. Then, as the debris cloud blocks sunlight, the water vapor condenses and falls as snow. Lots of snow. You're looking at blizzards across temperate zones in the middle of summer. If this happened at a different time of year, the climate whiplash alone would devastate ecosystems. So could we see it coming in time to do anything? That's the question that keeps planetary defense scientists up at night. Remember? Trino. Atlas was spotted in October 2024, and its closest approach is December 2025. Roughly 14 months of warning. Sounds like a lot. Right, but here's the brutal reality if it were on a collision course. 14 months is nowhere near enough time to mount a meaningful defense with current technology. NASA's DART mission, the one that successfully deflected the asteroid Dimorphos in 2022, took years of planning and required a relatively slow-moving target. DART impacted Dimorphos at 6. 6, so 3i. Atlas is moving nearly 5 times faster. The kinetic energy you'd need to deflect it is staggering, and the precision required is beyond anything we've attempted. Lindley Johnson, NASA's former planetary defense officer. Put it bluntly, in a 2019 interview, if we discover an object with less than a year until impact, our options range from very limited to none. And that was for near-Earth asteroids we've been tracking for decades. An interstellar intruder coming from a blind spot. We'd be using the technical term completely screwed. But here's the thing, we're not. 3I. Atlas is missing us by 5 million miles. The calculations are solid. The trajectory is locked in. December 19th. 2025 will be a day of wonder. No terror. But that hypothetical scenario we just walked through isn't science fiction. It's a mathematical certainty that, eventually, something like this will be on a collision course. The question isn't if, it's when, and whether we'll be ready. Which brings us to the uncomfortable truth about how we almost missed 3I, Atlas, in the first place. And why our current detection systems have gaps big enough for a city-sized object to slip through unnoticed. Here's the part that should terrify you. We got lucky with 3I, Atlas. Incredibly lucky, because our planet-wide system for detecting incoming threats has a massive, glaring blind spot. And this object came at us from exactly that direction. Let me explain how we actually watch the sky for dangers. Right now, humanity's asteroid detection network consists of a handful of ground-based telescopes scattered across the globe. The big players are NASA's Atlas System 4 telescopes in Hawaii and South Africa, the Catalina Sky Survey in Arizona, and Pan-STARRS, also in Hawaii. These telescopes work by repeatedly photographing the same patches of sky, night after night, then using software to detect anything that moves between images. It's basically a cosmic game of spot the difference, and it works brilliantly for objects already in our solar system, orbiting predictably around the sun. But here's the problem, all of these telescopes are on Earth, obviously, and Earth orbits the sun, also obvious. But think about what that means for a second. For roughly half of the sky, the half in the direction of the sun, we're effectively blind. You can't point a telescope at the sun and expect to see anything except a fried camera sensor on a very expensive repair bill. There's a massive cone of space stretching from Earth toward the sun and beyond, where objects can approach almost undetected until they move into a position where sunlight isn't overwhelming our instruments. 3I. Atlas approached from almost exactly that direction. For weeks, it was hidden in solar glare, invisible to ground-based surveys. By the time it moved into a patch of sky dark enough to observe, it was already well inside the orbit of Mars. Dr. Larry Dano, one of the lead scientists on the Atlas project, described the discovery as catching something that had already broken into the house. We didn't spot this thing approaching from deep space. We found it when it was practically on our doorstep. Now, you might be thinking, okay, but we did eventually spot it. Right, system worked. Sure. This time. Because 3I, Atlas wasn't on a collision course. But let me tell you about July 25th. That's when an asteroid designated 2019 OK screamed past Earth at a distance of just 45. 0, 0, 0 miles. About 1/5 the distance to the moon. That's closer than some satellites. And we didn't detect it until the day before. 24 hours of warning for a 100-meter rock that, if it had hit, would have released energy equivalent to 30 Hiroshima bombs. Why did we miss it? Same reason. It came from the direction of the sun. Michael Brown, an associate professor at Metz University who studied the event, said in an interview, "This one came out of a blind spot. We had no chance of seeing it until it was almost too late. The asteroid was traveling at 54 km/h, moving across the sky too fast for most survey telescopes to track properly. By the time astronomers realized what was happening, it had already passed us. We literally watched our potential doom fly by in the rear-view mirror." Here's another fun fact that'll keep you up at night. NASA estimates there are roughly 25,000 near-Earth asteroids larger than 140 meters, big enough to cause regional devastation. As of 2024, we found and cataloged about 40% of them. That means 500 potentially city-killing rocks are out there orbiting the sun, and we have no idea where they are. Some of them are probably in orbits that bring them uncomfortably close to Earth every few years. And we just haven't been looking in the right place at the right time to spot them yet. And that's just asteroids native to our solar system. Objects that follow predictable paths and return on schedule like cosmic clockwork. Interstellar objects like 3I, Atlas. We have no predictive capability whatsoever. They come from random directions at random times, moving at speeds that dwarf anything gravitationally bound to our sun, until one enters our solar system and gets close enough to reflect sunlight we can detect. It's essentially invisible. We're talking about objects that could be spotted months before arrival at best, or weeks at worst. So how do we fix this? The solution sounds simple: put telescopes in space, where they're not limited by Earth's daylight cycle, and can observe in all directions continuously. And we're actually working on it. NASA's NEO Surveyor mission, short for Near Earth Object Surveyor, is a space-based infrared telescope specifically designed to find asteroids. It's scheduled to launch in 2027, and it's positioned at a gravitationally stable point between Earth and the Sun. We let it observe objects approaching from the sunward direction that ground telescopes can't see. According to NASA's projections, NEO Surveyor could catalog 90% of near-Earth asteroids larger than 140 meters within a decade of operation. But here's the catch: it's not launched yet, and it's been delayed multiple times due to budget constraints. The current projected cost is around $1, $2 billion, over the mission's lifetime. That sounds like a lot, until you realize that in the say, military spends more than that on a single B-2 stealth bomber. We're talking about a system that could provide early warning of civilization-ending impacts. And it's been chronically underfunded and delayed because, frankly, asteroid defense doesn't win elections. Let's talk about detection speed, because that's the other critical factor. Even with perfect sky coverage, you still need time to confirm that something is actually a threat. When a new object is spotted, astronomers need multiple observations over several days or weeks to calculate its orbit accurately. That's not paranoia. That's physics. A tiny error in measuring an object's position translates to massive uncertainty in where it'll be months later. You need enough data points to plot a reliable trajectory. And that takes time. With 3i, Atlas, astronomers had the luxury of 14 months between detection and closest approach. That's an eternity in asteroid tracking terms. But remember 2019, okay, 1 day of warning. And here's the nightmare scenario that keeps planetary defense experts awake. What if an interstellar object approached from the sun's direction on a collision course, and we only spotted it when it was a week out? What do you even do with that information? The honest answer is not much. You alert governments. You warn populations in the predicted impact zone. You hope the calculations are wrong and it misses. But mounting any kind of physical defense in a week, impossible. Even getting a spacecraft off the ground takes months of preparation. You need to calculate trajectories, fuel the rocket, run systems checks, coordinate with international partners. A week might be enough time to evacuate a city if you're lucky, and people don't panic. There's nowhere near enough time to stop the impact. This is why organizations like the Planetary Defense Coordination Office exist. Yes, that's a real office at NASA. Established in 2016. Their entire job is to find, track, and characterize potentially hazardous asteroids, and to coordinate an international response if we ever face a real threat. But they'll be the first to tell you their capabilities depend entirely on early detection. Give them 5 years of warning, and they can potentially deflect an asteroid. Give them 5 months, and options start running out. 5 weeks, you're looking at emergency preparedness, not prevention. And there's one more layer to this problem: false alarms. Say, every time we spot a new near-Earth object, there's a brief window where the uncertainty in its orbit is massive. Sometimes an asteroid will initially appear to have a small chance of hitting Earth, only for additional observations to rule out impact entirely. This happens multiple times per year, and has led to a kind of detection fatigue. News outlets report asteroid might hit Earth, then quietly update the story when better data shows it'll miss. The public gets desensitized. So when a real threat eventually appears, will anyone take it seriously? The scientific community has tools to handle this. NASA's Sentry system continuously monitors all known near-Earth objects and calculates impact probabilities. The Torino scale rates threats from 0 to 10, based on collision likelihood and potential damage. But these systems are only as good as the data feeding into them. Miss the initial detection because an object came from a blind spot, and none of those tools matter. So where does that leave us? With 3i, Atlas, we found it. We tracked it. We know it is not a threat. But the fact that an interstellar object could slip inside Mars's orbit before we spotted it should be a wake-up call. The gaps in our detection grid aren't theoretical. They're real. They're exploitable. And eventually something dangerous is going to come through one of them. But let's assume for argument's sake, that we did have perfect detection 5 years of warning before an interstellar object arrived on a collision course. Could we actually stop it? Or would we just have 5 years to watch our doom approaching? Powerless to change the outcome. This is where Hollywood has done us a massive disservice. You've seen the movies Bruce Willis drilling into an asteroid, nuclear bombs saving the day, heroes flying spacecraft into the heart of danger. It makes for great entertainment, but it sets up catastrophically wrong expectations about what we can actually do if a planet killer is heading our way. Let's start with the good news: we're not completely helpless. On September 26th, Liang Chen-Ling Arshar, humanity proved for the first time in history that we can change the trajectory of an asteroid. NASA's DART spacecraft double asteroid redirection test slammed into a small asteroid moon called Dimorphos at 1. Boncham Mpefa. The impact was spectacular. Telescopes around the world watched as debris exploded outward from the collision site. And when scientists measured Dimorphos' orbit afterward, they found something incredible. The asteroid's orbital period had changed by 33 minutes. DART had successfully nudged the celestial body off its path. Dr. Nancy Shabao, DART coordination lead at Johns Hopkins Applied Physics Laboratory, called it humanity's first step in learning to defend ourselves from a cosmic impact. And she's right. It was a monumental achievement. But here's what the headlines didn't emphasize. Dimorphos was the perfect target. It was relatively close, only about 7 million miles from Earth at impact. It was moving slowly in cosmic terms. And critically, we weren't trying to deflect it away from Earth. We were just testing whether we could change its orbit at all. The stakes were scientific, not existential. Now let's talk about 3I, Atlas. Could we dart it if we had to? The short answer is probably not. Here's why. DART worked because of something called momentum transfer. The spacecraft weighed about 120 pounds and was traveling at 6 kilometers per second when it hit. When you multiply mass times velocity, you get momentum. And when DART transferred its momentum to Dimorphos, the asteroid's velocity changed ever so slightly. But remember that word, slightly. We're talking about a velocity change measured in millimeters per second for an asteroid already on a safe orbit. That tiny nudge is enough. Give yourself years of lead time, and a millimeter per second change compounds into thousands of miles of deflection by the time the asteroid reaches Earth. It's like redirecting a train move the track just a few inches when the train is miles away. And by the time it reaches the station, it's on a completely different platform. But 3I, Atlas is moving at 31 kilometers per second. That's nearly 5 times faster than Dimorphos was moving relative to DART. And it's significantly larger. Remember, we estimated 450 meters in diameter, compared to Dimorphos' 160. Bigger size means more mass. More mass means more momentum, and the faster something's moving, the harder it is to change its trajectory. You'd need a much bigger impact to achieve the same deflection. How much bigger? Let's do some rough math. If you wanted to deflect 3I Atlas by enough to make it miss Earth and you only had a year of warning, you'd need to change its velocity by several meters per second. Not millimeters. That's thousands of times more momentum transfer than DART achieved. You'd need to hit it with something massive, moving incredibly fast. Or both. Which brings us to the option nobody wants to talk about. But everyone is thinking about nuclear weapons. And before you roll your eyes at the Hollywood cliché, hear me out, because the real science is both more interesting and more sobering than the movie show. Contrary to what Armageddon taught a generation of moviegoers, you don't drill into an asteroid and blow it up from the inside. That's absurd. What you actually do is detonate a nuclear device near the object, not on it. Near it, and use the energy from the explosion to vaporize part of the surface. That vaporized material gets away from the asteroid, and Newton's third law kicks in for every action. There's an equal and opposite reaction. The jetting material acts like a rocket engine, pushing the asteroid in the opposite direction. This isn't science fiction. It's a real concept called nuclear deflection, and scientists have been studying it for decades. A 2007 NASA study titled Near-Earth Object Survey and Deflection Analysis of Alternatives examined nuclear deflection as one of several options. The conclusion is stark for large asteroids on short warning clocks. Nuclear deflection is, on paper, the most effective tool we currently have. A single 1 megaton device, detonated at precisely the right standoff distance, could dump enough energy into the surface to nudge an incoming object meaningfully off course. But in this is a massive, but it demands almost unreal precision. Detonate too close, and you risk shattering the body into multiple fragments that are still headed away. No. Instead of one impact, you've created a swarm. Detonate too far, and the blast blooms harmlessly into vacuum, doing nothing useful. You need to know the object's composition, spin, and structural strength with brutal accuracy. You have to calculate the exact distance and the exact orientation for the detonation. And then you have to deliver that warhead to the right point in space millions of miles away at the exact right moment. Like threading a needle while everything is moving. Oh, and there's one more tiny problem in international law. The Outer Space Treaty of 1967, signed by over 110 countries, including the United States and Russia, explicitly bans placing nuclear weapons in space. Yes, there are provisions for extraordinary circumstances. But can you imagine the negotiations required to get global consensus on launching nukes into orbit while a planet killer is bearing down? The bureaucracy alone could become its own kind of doom. Still, let's assume we clear every hurdle. We build a nuclear deflection mission, launch it, and successfully intercept 3 Tuatalas. Here's the next problem. Interstellar objects aren't like the near-Earth asteroids we've been cataloging for decades. We know almost nothing about what they're truly made of. It's 3I. Atlas, a solid monolith, a loose rubble pile, a fragile, ice-rich comet nucleus. The strategy changes dramatically depending on the answer. If it's a rubble pile, basically smaller rocks loosely held together by gravity, then an impact, nuclear or otherwise, might just scatter it without changing the overall trajectory much. The fragments would keep sweeping along roughly the same path. And you've turned one problem into 100 smaller problems. If it's a dense, solid chunk, momentum transfer works cleanly and efficiently. But if it's a comet wrapped in thick ice, nuclear heating could trigger catastrophic outgassing thrust in unpredictable directions that makes the trajectory harder, not easier, to control. And then there's a timeline. DART took nearly 10 years from initial concept to launch, 10 years of planning, engineering, testing, and prep to hit a target we'd studied for years beforehand. With 3, A2, Atlas, we'd have had 14 months from detection to impact in the nightmare scenario. You simply can't design, build, test, and launch a full planetary defense mission in 14 months with today's infrastructure. Not reliably, not at scale. So what about other options? There's the gravity tractor concept, a spacecraft flying alongside an asteroid, using its tiny gravitational pull to slowly tug the object off course. It's elegant. It's controllable. It requires 0 explosives. The problem is that it's painfully slow. You'd need years, maybe decades of steady operation to accumulate enough deflection. Great for an object spotted 50 years out. Useless for something 14 months away. There's laser ablation, powerful lasers vaporize surface material, creating thrust by the same rocket exhaust principle as nuclear deflection, just gentler and more precise. NASA studied it. The engineering is enormous, but it's not fantasy. And again, it's a long lead solution. You'd need sustained laser fire over months or years. Some researchers propose kinetic impactors too, not one dart-style hit, but a fleet of them, striking in sequence, each impact stacking a little more deflection onto the last. That could work in theory for something like 3I, Atlas. But building and launching multiple spacecraft on short notice brings us right back to the same trap time. Here's what it all boils down to. Planetary defense is like car insurance. It only helps if you already have it before the crash. With native solar system asteroids, we can often track them decades ahead, giving us time to respond. Interstellar objects are different. They're like a drunk driver, running a red light at 100 miles an hour by the time you see them. Your window to react is already closing. Tom Stutler, NASA's DART program scientist, said something after the impact that stuck with me. DART proved we can move an asteroid. What it didn't prove is that we can do it fast enough when it truly matters. And that's the uncomfortable truth. We've taken a first step in defending Earth, but we're nowhere near ready for a real crisis, especially one involving something that comes screaming in from interstellar dark. So if we can't reliably stop 3I, Atlas in the nightmare version of this story, what could we actually do with 14 months of warning? The answer is practical, and a little unsettling. It starts with learning what this visitor is made of, which pulls us into some truly bizarre physics. Understanding what 3X Atlas is made of isn't just academic curiosity. It's the difference between predicting its behavior and being blindsided by something we never saw coming. And right now, this object is doing things that make scientists quietly uneasy. So let's begin with what we can actually observe. When astronomers point telescopes at 3I Atlas, they're not just taking pretty pictures. They're doing spectroscopy breaking reflected light into its component wavelengths. Different chemicals absorb and emit at specific wavelengths, leaving a signature like a fingerprint. It's CSI for space rocks. In 3I, Atlas's fingerprint is telling a strange, layered story. The spectra show clear signs of water vapor, carbon dioxide, and carbon monoxide outgassing as the object warms on its way toward the sun. That's classic comet behavior. Comets are dirty snowballs, ice mixed with dust and rock, awakening as sunlight heats them. So far, so normal. But here's where it gets odd. The ratios of those gases don't match any comet we've studied up close in our own solar system. Dr. Alan Fitzsimmons of Queen's University Belfast, who studied 2I, Borisov, in detail, noted that interstellar comets can be chemically alien to our expectations because they formed around different stars, under different conditions. With 2I, Borisov, they found carbon monoxide concentrations 9 to 26 times higher than typical local comets. That was our first clear hint that other systems cook their ingredients differently. But 3I, Atlas is hinting at something stranger still. The amount of gas it's releasing doesn't line up cleanly with the brightness changes we're seeing. Normally, as a comet outgasses, it builds a coma fuzzy halo of gas and dust, and the brightness rises in a fairly predictable way. With 3I, Atlas, the brightness flickers and fluctuates, suggesting the surface isn't uniform. Some regions may be coated in highly reflective ice, while others are darker, rocky patches. As it rotates, different faces turn toward the sun, and the activity swings with them. Rotation itself becomes another puzzle. From those brightness variations, astronomers estimate 3I Atlas spins once, roughly every 8 to 12 hours, still refining the exact period. That's fairly fast for an object this size. And it matters. If the body were a loose rubble pile, spinning that quickly could tear it apart from centrifugal forces. The fact that it's staying intact suggests real internal strength, or a cohesion mechanism we don't fully understand yet. Think back to Oumuamua. Remember how its unexplained acceleration set off years of debate, dozens of hypotheses, invisible hydrogen outgassing, bizarre tumbling, strange shapes amplifying thrust, or at the wild edge an artificial light sail. Harvard's Avi Loeb argued seriously for that last possibility, and most of the field pushed back hard. But the uncomfortable part remains, we still don't have a universally satisfying natural explanation for Oumuamua's behavior. And now 3I, Atlas is showing its own echo of that mystery, the same kind of extra acceleration, that lingering 15% we can't neatly account for. It feels familiar in the way a half-remembered dream feels familiar. One explanation gaining traction involves super volatile materials that vaporize at extremely low temperatures. Local comets typically outgas water, carbon dioxide, and carbon monoxide as they warm. But what if interstellar comets carry large stores of molecular nitrogen ice, or carbon monoxide ice, that can sublimate far from the sun in regions so cold and distant that the outgassing is nearly invisible to our instruments? The thrust would still be real. The push would still add up, but the jets might be too faint, too diffuse, to see clearly. A 2020 study in Nature Astronomy from researchers at Yale explored this for Oumuamua. They calculated that if the object were mostly nitrogen ice, something like the surface composition of Pluto's moon Triton, then sublimation could explain the acceleration without visible jets. It's an elegant idea, but it comes with a catch. Nitrogen ice doesn't like sunlight. It sublimates quickly when heated. If Oumuamua were nitrogen-rich, it should have lost a dramatic fraction of its mass during its solar flyby. Yet, observations didn't show the extreme brightness changes you'd expect from something rapidly evaporating away. So what does that imply for 3I? Atlas, it may be that we're only seeing part of the engine. Visible outgassing water and carbon dioxide could be blooming on sun-facing regions, while super volatile sublimation occurs elsewhere, producing thrust we can measure but not directly observe. It's like watching a boat from shore. You see the wake on the surface, but you don't see the propeller turning beneath. And then there's the journey itself. 3I, Atlas may have traveled through interstellar space for millions of years. What does that do to an object? Interstellar space isn't empty. It's laced with cosmic rays, high-energy particles that steadily bombard exposed surfaces over long timescales. Radiation can alter chemistry, turning simple ices into more complex organics, and rearranging mineral structures. By the time an interstellar object arrives, its skin may be radically different from its interior. Some researchers call this cosmic weathering. One hypothesis suggests Oumuamua developed an organic rich crust over immense time, a kind of radiation-baked shell. When it neared the sun, that crust may have reacted in ways that didn't match pristine ice or bare rock. If 3I, Atlas carries a similar travel-worn surface, it could explain why its behavior refuses to fit our neat, local categories. But here's the part that keeps astronomers honest. We'll never get a close-up. We won't lend a proof. We won't drill. We won't bring home a sample. By the time we finish analyzing the December 19th data, 3I, Atlas will already be racing back into the dark between stars. Gone forever. Everything we learn must be teased out from telescopic measurements made during a brief, irreplaceable flyby. And those measurements are limited by distance and by physics itself. Even the James Webb Space Telescope, as powerful as it is, can only resolve so much detail at these ranges. We can estimate the overall shape, likely elongated, as many comets are, but we can't map fine surface features. We can measure total gas output, but not always pinpoint exactly where each jet originates. It's like diagnosing a patient through frosted glass, guided by shadows and heat and hints. There's one more layer to the mystery, not which star system it came from, but where within that system it formed. In our own solar system, formation distance matters. Inner regions yield rock and metal. Outer regions preserve volatile ices. The chemistry we're seeing suggests 3I. Atlas likely formed far from its parent star. An analog to a Kuiper belt, then got flung out during some violent gravitational reshuffling. Perhaps giant planets migrating like slow wrecking balls. It wandered for ages, collecting that cosmic weathering, until our sun's gravity curved its path inward for this one. Breathtaking pass. But while spectroscopy and orbital mechanics can tell us a lot, they can't answer the question. Most people are quietly asking, what will it look like when it goes by? Will you be able to see it, and what? Exactly. Will scientists do in the narrow window when it's closest? Let's talk about December 19th in real, grounded terms. What will it actually look like from your backyard? Can you step outside and watch an interstellar visitor slide past the stars? The honest answer is going to disappoint some people, probably not with your naked eye. Based on brightness predictions, 3-2. Atlas will likely peak around magnitude 10 to 12 at closest approach. If you're not used to the magnitude scale, it runs backward. Lower numbers are brighter, under perfect dark skies. The faintest stars visible to the naked eye are around magnitude 6. Venus blazes far brighter than that. Magnitude 10 to 12 is firmly telescope territory. You'll need a decent backyard telescope, something around a 6-inch aperture, or larger plus dark skies away from city glow, to have a real shot. But here's what makes it special for amateurs: it won't sit still. Unlike a star, 3I, Atlas will move. First, through a telescope. You should be able to watch it drift across the field of view over minutes. Planets shift, sure, but over days and weeks, not live. Not like this. Seeing 3I, Atlas will feel like catching a distant aircraft through your optics, except it's a half-kilometer shot of ice and rock from another star system, traveling around 7,000 miles an hour. The best view in geometry favors the southern hemisphere near closest approach Chile, Australia, South Africa. Northern observers won't be shut out, but you'll be dealing with a lower horizon and more atmospheric blur. The big professional facilities, Hawaii, the Canaries. Chile will carry the cleanest views, and even if you never spot it yourself, you'll be able to watch it live. NASA has already planned streams from multiple observatories during the flyby. ISO's very large telescope will track continuously, as will Gemini and Subaru. These instruments can capture objects far fainter than any backyard scope, feeding real-time imagery and measurements to scientists worldwide. But the real story is happening in wavelengths your eyes can't see. Webb will watch 3I, Atlas, in infrared heat. That's how you map temperature differences across the surface, which hints at composition and structure. Is one región hicier, are jets erupting from specific areas. Infrared lets us infer those answers with quiet confidence. Hubble is also getting time. It's older than Webb, but still astonishingly capable in visible and ultraviolet light. Ultraviolet is especially useful because many comet gases fluoresce after sunlight breaks, molecules apart. Hubble can map that faint UV glow and help locate active outgassing regions with far more detail than visible images alone. Most people don't realize how competitive telescope time is. Astronomers submit proposals months ahead, and committees choose only a fraction. The fact that 3I, Atlas is booked on Webb, Hubble, and major ground-based giants tells you how seriously the community is taking this moment. It's astronomy's version of a rare eclipse. Everyone wants their instrument pointed at it. So what are they trying to learn first? The basics, the exact size and shape. Right now, estimates from 300 to 600 meters leave too much uncertainty. Close approach imaging should narrow that range. Second, the precise rotation period because spin reveals structure solid monolith or rubble pile. Third, the chemistry every molecule detected is a clue about the birthplace conditions in another star system. There's also a careful search for complex organic molecules, carbon-based compounds that are the raw building blocks of life. And before anyone leaps to conclusions, organics don't equal aliens. Organic chemistry happens naturally in space all the time, but it tells us something profound about what other systems can produce us, and what kinds of ingredients drift between the stars. In a way, 3I. Atlas is a messenger, even if it never speaks, carrying a chemical postcard from somewhere we may never identify. And on December 19th, for a few precious hours, we get to read what we can from that postcard before it slips back into the dark. Because whether the answers feel comforting or unsettling, they'll be real written in spectra, in heat maps, in the tiny deviations of motion that our instruments can measure, even when our eyes cannot. And if this object is stranger than our models, if it carries supervolatiles, radiation-baked crusts, or structures we haven't named yet, then the data from this flyby won't just be interesting. It could force us to redraw the quiet boundaries of what a comet even means. That's why every major telescope is lining up like a choir, waiting for its cue. Not for drama, not for panic, but for clarity slow, careful, and earned. And that clarity matters. Because the next interstellar visitor might not give us 14 months. It might not give us mercy. So we watch this one closely, gently, and without looking away. We measure its breath of vapor. We track its spin. We weigh its brightness against its push. We do the quiet work of science because quiet work is how you survive a loud universe. And in the end, the goal is simple. Know what it is, know what it does, and know what we do if luck ever stopped favoring us. Because the more we understand this visitor, the less we're guessing and the less we're guessing, the safer we become, one careful observation at a time. If 3I, Atlas is rich in complex organics, it hints that the system it came from ran chemistry, not so different from the pathways that eventually led to life on Earth. Dr. Martin Cordiner, an astrochemist at NASA's Goddard Space Flight Center, who led a study on 2I, Borisov's composition, said something that stayed with me. Every interstellar object is a sample return mission we didn't have to pay for. Let that settle in. We spend billions sending spacecraft to nearby comets and asteroids just to bring back grams of dust. But these visitors arrive on their own, drifting right up to our doorstep, carrying physical evidence from entirely different star systems like a quiet gift from a distant chemistry lab. We can't touch them, but we can study them in ways we can't study anything light years away. And there's a genuinely exciting citizen science angle here. Amateur astronomers with mid-sized telescopes can contribute real, usable data. Groups like the American Association of Variable Star Observers are coordinating observation campaigns. If you've got a telescope, a decent camera, and clear skies, you can upload your measurements to a central database. Professionals can use that stream of observations to fill in the gaps because even the biggest observatories can't stare at one target 24/7. When Hubble has to slew to another object, or when clouds roll over Chile, the chain can break. But amateurs in different time zones can keep it alive. handing the sky off like a relay race quietly, steadily, through the night. Here's why that matters in practice. When Oumuamua passed through in 2017, there were only a handful of days when it was bright enough for detailed study. Scientists had to coordinate observations across multiple telescopes just to build a coherent dataset, and even then, coverage gaps left key questions hanging. With 3i, Atlas, the astronomy community is determined not to repeat that mistake. The plan is continuous coverage from detection through closest approach and beyond, tracking it for as long as physics allows before it fades into the dark. One of the most ambitious goals is measuring the object's mass. You can't put a comet on a scale, obviously. So how do you weigh something that never slows down for you? The trick is to watch how it responds to gravity. As 3i, Atlas passes relatively close to Earth, about 5 million miles our planet's gravity will ever so slightly bend its path. By measuring the exact change in velocity and direction, scientists can work backward and estimate its mass. It's like watching a billiard ball glance off another and using the reflection angle to infer how heavy each one must be. Mass matters because density is mass divided by volume. If you know the size and the mass, you can compute average density, and density points straight toward composition. If 3i, Atlas comes in around 5 grams per cubic centimeter. It's probably a fluffy mix of ice and dust. If it's closer to 2 or 3 grams per cubic centimeter, there's a lot more rock in the recipe. Suddenly, you're not guessing whether it's a pristine cometary body or something more processed and stone-heavy. There will also be radar observations, which are especially fascinating because radar is one of the few ways we can probe surface texture beyond what visible light suggests. Arecibo in Puerto Rico used to be the gold standard for asteroid radar before it collapsed in 2020. But the Goldstone Deep Space Communications Complex in California is still operational and still powerful. Radar works by bouncing radio waves off the object and studying the echo. The time delay gives distance with incredible precision, and the way the signal scatters reveals surface roughness. Smooth ice reflects differently than jagged rock, but there's a hard limitation: radar range drops fast. For Goldstone to get useful data, 3i, Atlas needs to be within a few million miles. It will be, but only briefly. The radar window is measured in hours, not days. That's why coordination is everything. Every observatory, every amateur station, every dish and detector has to be timed like choreography, squeezing the maximum amount of data out of the flyby. And when it's over, when 3i, Atlas has whipped past Earth and is accelerating back toward the outer solar system, scientists will be left with terabytes of measurements and years of analysis. Doctoral theses will be written about this single object. We'll learn about planetary formation, star system evolution, and the chemistry of interstellar space in ways we can't learn any other way. But beyond the science, something quieter is happening too. On December 18th, humans around the world will be watching an object from another star, an uninvited piece of cosmic real estate slipping through on a journey that began in a place we'll never visit. It's a reminder of how vast the universe really is, and how small our corner of it remains. And that raises an unsettling question: if objects like this pass through at all, what else is out there that we simply haven't noticed yet? The uncomfortable truth is that 3i, Atlas is probably not alone. In fact, it's almost certainly not. Right now, as you're listening to this, there may be dozens, maybe hundreds of interstellar objects inside our solar system that we've never detected. The math behind that idea is both fascinating and faintly unnerving. In the span of 8 years, between 2017 and 2024, we confirmed 3 interstellar objects: Oumuamua, Dvai, Borisov, and now 3i, Atlas. 3 confirmed visitors in 8 years, but our detection capabilities are laughably incomplete. We only catch the ones that pass close enough, shine brightly enough, and happen to be in a patch of sky we're actively serving at exactly the right moment. It's like standing in a dark forest with a flashlight and assuming you've seen all the animals because you spotted 3 deer. In 2019, a team of researchers at Harvard, led by Amir Siraj, published an estimate in the Astrophysical Journal, letters attempting to infer how many interstellar objects actually pass through the inner solar system, using the detection rates of Oumuamua and 2i, Borisov. Their calculations suggested that at any given time there could be roughly 100 interstellar objects closer to the Sun than Neptune. 100, and we found 3. Sit with that ratio for a moment. We might be detecting only a tiny fraction of what's truly out there, missing the rest because they're dim. fast, or hidden in our observational blind spots, like noticing one mouse in your kitchen and not realizing how many more are inside the walls. The size distribution makes it even wilder. Most interstellar objects are probably small meters, not hundreds of meters. Those are nearly impossible to spot unless they pass extremely close to Earth. But the models suggest that objects around 100 meters and larger could sweep through the inner solar system multiple times per year. We're just not seeing them because our surveys aren't sensitive enough. Or they come from directions we aren't monitoring. Or they move too quickly for our systems to flag them as interesting before they're already leaving. And then it gets stranger. Some scientists think a few interstellar objects might not just pass through, they might get captured. Imagine a wanderer arriving at just the wrong angle and having a close gravitational encounter with Jupiter or Saturn under very specific conditions. That kind of encounter could steal enough speed to trap it in a bound orbit around the sun. It would stop being hyperbolic, escape traffic, and become a permanent resident, indistinguishable from native objects, unless you know exactly what dynamical fingerprints to look for. Dr. Fatih Namouni at the Côte d'Azur Observatory in France has studied this scenario. In 2018, he and colleague Maria Helena Moraes published research suggesting that certain asteroids with unusual retrograde orbits, meaning they orbit opposite the planet's direction, could be captured interstellar objects. One candidate is 2015 BZ 509, which shares Jupiter's region but loops around the sun backward. Its dynamics suggest it didn't form here. It's an immigrant, trapped long ago. How many other interstellar refugees are hiding in our catalogs, we don't know. We've logged over 1 million asteroids, but only a small fraction have undergone that level of forensic orbital analysis. There could be hundreds, maybe thousands of former wanderers in plain sight, waiting for someone to ask the right questions. Now zoom out further. The Milky Way holds over 100 billion stars, and many of them have planetary systems. During the birth of each system, gravitational chaos ejects objects, countless icy bodies flung outward like sparks from a grinding wheel. We know this happened here. Models suggest that in our own early solar system, as Jupiter and Saturn migrated, enormous numbers of objects were thrown into interstellar space. Multiply that process across the galaxy and you get a staggering result, perhaps on the order of 10, 26 interstellar objects, wandering the Milky Way, frozen leftovers scattered through the dark like grains in an ocean. Most are small comet-sized, asteroid-sized, boulder-sized, but statistically, some must be huge rogue planets, even planet-mass worlds, drifting without a sun. And while the odds of a truly massive close encounter are vanishingly small on human timescales, smaller debris is a real, constant train. Our solar system is traveling through the local bubble, an enormous, low-density region of hot gas about 1,000 light-years wide, likely carved by ancient supernovae, and those explosions would have scattered debris across a vast volume of space. Some of that debris may still be drifting out there, and we may be brushing past it even now, quiet reminders that our solar system isn't sealed. It's porous. What's especially unsettling is the detection lag. Remember, we only spotted 3I, Atlas, in October 2024, and it sweeps past Earth in December 2025, just 14 months of warning. Now picture an object on a similar track, but smaller, maybe 200 meters instead of 450. It would be dimmer, easier to miss, like a faint coal floating in the bright wash of dawn. We might not notice it until it's only months away, or weeks. What do you do with information like that? Here's the scenario that keeps planetary defense teams awake: a 150-meter interstellar object, approaching from the sunward direction. Detected 3 weeks before closest approach. Early orbit fits show a 5% chance of impact. Not a verdict, just a trembling margin that takes more nights of data to shrink. Not guaranteed, but not trivial. You can't evacuate entire continents on a 5% probability. You can't launch a deflection mission in 3 weeks. All you can do is keep observing, tighten the math, and hope uncertainty collapses in your favor while the object keeps coming. Indifferent to our sleep schedules. That isn't science fiction. It's a plausible outcome given today's detection limits and the estimated traffic of interstellar visitors. And it gets worse once you factor in velocity. Our planetary defense playbook, what little we have, was built for near-Earth asteroids moving around 10 to 25 kilometers per second. Interstellar objects can arrive at 30. 0. Even 50 kilometers per second relative to Earth. The faster the visitor, the less time you have, and the harder it is to push it aside. Because the needed shove scales brutally. The galaxy is sending us packages we never ordered. And most of them arrive with no tracking number at all. Only a brief glint as they slip into our neighborhood. 3. iAtlas is one we happened to catch early enough to study. But statistically, there are others out there right now, some of them closer than this one, and we simply don't know they exist. Which brings us to the uncomfortable but necessary question. What are the real odds that something catastrophic is headed our way? And how do those odds compare to other existential risks? Let's talk numbers, real numbers, because asteroid impacts attract a lot of dread and not enough careful risk. Accounting you can actually live with. So what are the chances that something native to our solar system or arriving from beyond it actually hits Earth and causes serious damage? NASA's Near-Earth Object Program has tracked threats for decades, and they use the Palermo Technical Impact Hazard Scale, a logarithmic measure that blends impact probability with kinetic energy into a single risk rating, one shared yardstick for very different kinds of danger. Anything with a Palermo value above about 2 is worth watching closely. 0 means the risk exceeds the background risk from all other similarly sized objects. As of 2024, there are exactly 0 known objects with the Palermo value above 0 threatening Earth in the next century. But context matters, because 0 today is not the same as 0 forever. It only means that, for the moment, the math looks calm. The dinosaur killer we mentioned earlier was a once in 100 million years kind of event, written into rock layers and sudden absences in the fossil record. Objects around 10 kilometers wide strike Earth on average every 100 to 200 million years. Based on the crater record, the last one was 66 million years ago, so statistically, we're not due anytime soon. Smaller impacts are more common. Tunguska in 1908. An object perhaps 50 to 60 meters wide flattened roughly 2,000 square kilometers of forest and represents events that occur on the order of every 300 to 500 years. Chelyabinsk in 2013. About 20 meters. Happens roughly once every 60 years, a flash, a shockwave, and then the sky goes quiet again. And tiny meteors burn up harmlessly in our atmosphere by the thousands every day. Brief silver stitches in the dark. Here's the key point. We've gotten fairly good at tracking the big ones. NASA estimates we've found over 95% of near-Earth asteroids larger than 1 kilometer the civilization-threatening class. The ones we haven't found are likely on orbits that don't come near Earth, or we would have spotted them by now. So the existential level threat from native asteroids is relatively low. But interstellar objects change the math, because the odds I just gave you assume predictable orbits we can monitor for decades. Like familiar hands on a clock, interstellar visitors are random encounters. They aren't neatly folded into the usual statistical model, because we don't truly know how many there are or how often their paths thread the inner solar system in ways that could threaten Earth. Still, we can try a rough estimate from the detection rate of Oumuamua, 2 Borisov, and 3I, Atlas 3 rare knocks on our door, correcting for how incomplete our surveys are. Researchers estimate an interstellar object larger than 100 meters passes within Earth's orbital distance roughly once per year. Most of those passages don't come close to Earth itself. Space is huge and Earth is a small target, but over a long enough timeline. One will eventually line up on a collision course. How long? Only very rough guesses. With big uncertainty, and the range narrows only as our eyes in the sky improve, with enormous error bars. An interstellar impact large enough to cause regional devastation might occur once every 10 million to 100 million years, similar ballpark odds to a Chicxulub scale native asteroid. The critical difference is warning time. We can predict native asteroids decades ahead. And years of lead time are everything. Interstellar objects give us months, at best. Possibly weeks. Gregory Laughlin of Yale, who has modeled interstellar encounters extensively, put it this way in a 2020 interview. The probability of an interstellar impact in any given year is vanishingly small, and the probability we'd have adequate warning if it happened is also vanishingly small. Low odds. Low warning, a cruel pairing. It's a double-edged risk, low probability. Catastrophic consequence. And minimal preparation time. So how does it compare to other existential threats climate change is unfolding on decade scales? COVID-19 reminded us pandemics are real and globally disruptive, arriving faster than we like to admit. Nuclear war is low probability. We hope. but entirely within human control to prevent or to trigger. AI risks are hotly debated with uncertain timelines. And then there's asteroid impact, low probability, high consequence, limited warning, minimal control. What makes asteroid defense unique is that it's entirely external to humanity and, with enough preparation, entirely preventable. We can't negotiate with a rock, but we can prepare to redirect it. We can't change its mind or appeal to its better nature, but we can detect it, track it, and potentially deflect it if we invest in the right systems. Which brings us to funding. NASA's Planetary Defense Coordination Office runs on roughly $150 million per year. That sounds big, until you realize it's under zero. 10% of NASA's total budget, and NASA itself is under zero. 5% of the federal budget. We spend about $20 per American per year on planetary defense. Compare that to roughly $800 billion on military defense. The priorities are revealing. And here's the kicker. The return on investment for planetary defense is, in a sense, infinite, because the payoff is continued history. If you successfully deflect a civilization-ending asteroid, you've saved everyone, every life, every economy, every future generation. The cost-benefit math is almost absurd. Even if the impact probability is 1 in a million in a given year, the expected value of prevention becomes enormous when you place 8 billion lives on the scale, plus all the lives that would have followed. But humans are famously bad at weighting low probability, high consequence risks. We worry about shark attacks, about 10 deaths per year globally, while ignoring asteroid threats that could kill billions. That bias has a name: probability neglect. Our brains didn't evolve it to think statistically about extinction. Because for 99.9% of human history, those risks didn't exist in forms we could predict or prevent. Here's the perspective shift. We are the first generation in Earth's 4 billion year story that can plausibly prevent its own extinction from an asteroid. Every mass extinction before us was unavoidable, no warning, no tools, no choice, and that's a strange new responsibility to carry. Dinosaurs couldn't build sky surveys or kinetic impactors. They died because a rock arrived, and there was nothing they could do. But we can. We have the technology, or we're close to detect threats and respond. DART probe we can change an asteroid's trajectory. Neo Surveyor. If it launches as planned, we'll close the detection gaps that let objects like 2019 OK slip past. And it will do it by watching in infrared, where glare can't hide as much. We're on the edge of making planetary defense almost routine, except we don't fund it like it's urgent. We treat it like background noise, someone else's problem. And the universe doesn't care about our budget cycles or election calendars. It just keeps sending objects through the dark. Let me give you a concrete scenario. Imagine it's 2035. An interstellar object is detected approaching from the sun's direction. First measurements arrive, like soft taps on a screen. It's 200 meters across, moving at 35 kilometers per second. And there's a 10% chance it hits Earth in 8 months. What happens next? In the current system, NASA alerts the International Asteroid Warning Network, a coalition of observatories worldwide. Everyone tracks the object to refine the orbit. Telescopes trade sleep for photons, and computers trade time for certainty. Within a week, that 10% either collapses towards zero false alarm or climbs. Say it climbs to 40%. Now you have a serious problem. The Planetary Defense Coordination Office convenes an emergency meeting, and the world suddenly feels smaller. They brief the White House, the United Nations, space agencies worldwide. Engineers at NASA and ESA run simulations. Can we launch a deflection mission in time with current capabilities? Probably not. 8 months isn't enough to design, build, test, and launch a spacecraft that can intercept a fast-moving interstellar target, especially one that doesn't behave like anything we've practiced on. So what do? You activate emergency protocols that have never been stress tested. You evacuate predicted impact zones, but orbital uncertainty means you might be evacuating the wrong continent. You mobilize disaster response, and you hope the probability estimate is wrong and it misses. Because hope becomes a policy when physics runs out. That's a scenario we're not ready for. And the maddening part is that we could be. The technology exists or is within reach. What's missing is political will and sustained funding to build the systems before we need them. Because once you need them, it's too late. Which leads to the philosophical question underneath all of this. How much should we spend to prevent a catastrophe that might not happen in our lifetimes? Our children's lifetimes? Or even our great-great-grandchildren's? Is it responsible to invest billions now against a threat that might not materialize after millennia? Or irresponsible not to? Knowing the threat is guaranteed eventually, the dinosaur killer didn't give them a choice. We have one. The question is whether we'll act before a clock starts ticking that we can't stop. And speaking of clocks, December 19th is coming fast. When 3I, Atlas makes its closest pass. Scientists will be watching with every instrument they can point, collecting data that might help us prepare for the day when an interstellar visitor isn't merely passing by. So what happens after December 19, when 3I Atlas completes its flyby and begins its return to the dark between stars? What comes next for the object itself, and for us? Start with the object's future. After closest approach, 3I. Atlas keeps accelerating as it heads away from the sun, taking a final gravitational assist as if it's borrowing a last push from our star. By the time it crosses Neptune's orbit sometime in late 2026, it'll be moving even faster than when it arrived, carrying momentum drawn from the sun's deep gravity well. Then it continues past the Kuiper belt, past the heliopause, where the sun's pull thins to almost nothing, back into interstellar space, within a decade. It'll be too faint for even our best telescopes to track, dissolving into the background like a dim star switching off, the way a signal fades when you step out of range. Within a century, it will be light years away. Within a few thousand years, it may brush another star system entirely, another distant sun with its own planets, and maybe, just maybe, astronomers there will spot it and wonder where it came from, the way we did. The thought experiment turns almost dreamlike when you follow it far enough. 3I. Atlas could travel for millions of years before another star's gravity significantly reshapes its path. It might drift through dozens of systems, quietly witnessing the birth and death of worlds carrying chemical fingerprints from the system where it formed. Like a message in a bottle that only matters if someone is watching at exactly the right moment. But for us, the story doesn't end on December 19th. That's when the real work begins. Every data set from the flyby has to be processed, cross-checked, and modeled. Teams will spend years pulling meaning from those photons and echoes, turning a brief pass into a library of results. Undergraduates today will write doctoral theses on 3I, Atlas. Papers will roll out through the late 2020s, analyzing everything from surface chemistry to outgassing rhythms to subtle trajectory perturbations. And whole careers will pivot around those measurements. And here's why this is especially valuable, 3I. Atlas is our third data point. In science, multiple examples create pattern. 1 point is an anomaly. 2 points hint at a trend. 3 points let you begin real comparison. Oumuamua was strange its acceleration. Its elongated shape, the lack of visible outgassing, and we never fully explained it. So conclusions stayed partly speculative. 2I. Borisov was more ordinary. It behaved like a comet, outgassed predictably, and fit our models reasonably well. But it was still only one typical example. Now we have 3I, Atlas, which seems to sit between the two outgassing like Borisov, yet showing unexplained acceleration, like Oumuamua. That's scientifically golden, because it suggests a spectrum of interstellar behaviors, not just two neat categories. Planetary astronomer Michele Bannister, who has studied multiple interstellar objects, said in a 2023 lecture, "Every interstellar object we detect teaches us something not just about that object, but about planetary system formation across the galaxy." And she's right. When you study 3I, Atlas, you're not just learning about one wandering rock. You're learning about conditions in another star system billions of miles away that created and ejected it in the first place. Think what that means for exoplanets. We've discovered over 500 exoplanets as of 2024, but they're all light years distant. And that distance is a hard wall. We can measure sizes and orbits, sometimes atmospheric chemistry if we're lucky, but we'll never visit them. We'll never hold a piece of them. Interstellar objects are the closest we'll ever get to sampling another star system directly. Every molecule of gas released by 3I, Atlas is physical evidence of chemistry happening around a different sun. There's also the question of improved detection. Each visitor teaches astronomers how to spot the next one earlier. After Oumuamua, surveys updated algorithms to flag hyperbolic trajectories faster. After Tuai, Borisov, they refined methods for distinguishing interstellar comets from long-period solar system comets. And after 3I, Atlas, there will be another round of upgrades. LSST de Verase. Rubin Observatory's legacy survey of space and time is scheduled to begin full operations in 2025. It's a game changer. LSST will photograph the visible sky every few nights with a camera so sensitive it can detect objects about 100 times fainter than current surveys. Researchers estimate that once LSST is running at full capacity, we may detect an interstellar object each year, maybe more. Instead of 3 in 8 years, we could have dozens within a decade. What will dozens teach us patterns in composition objects from particular regions of the galaxy may carry distinct chemical signatures. Each one is a quiet lesson, then it's gone. Patterns in size distribution are most of them tiny. Fleeting specks, or is there a hidden population of larger bodies we simply haven't caught yet? Patterns in trajectory. Do they arrive from every direction at random? Or do we see subtle clustering that hints at shared origins? And here's the thrilling part, with enough detections. We may be able to trace some of them back to specific star systems, following breadcrumbs that fade, but don't vanish into the dark. Right now, we can't say with certainty which star 3I Atlas came from, because the uncertainties in its path grow dramatically when you rewind millions of years. But if we spot an interstellar object early, track it with exquisite precision through its entire passage, and it happens to be relatively young, maybe only a few 100,000 years into its journey, we might actually pinpoint its origin star. Just imagine that. Imagine being able to say, calmly and clearly, this object came from Tau Ceti, or this comet was ejected from the planetary system around Epsilon Eridani. Names we've only whispered in textbooks and late-night lectures. Suddenly, you're not studying a random rock. You're studying a physical sample from a specific star you can point a telescope toward and observe. You could compare the object's chemistry to that star's spectrum and learn what planet formation looked like in that exact neighborhood. Some researchers are even proposing missions to intercept interstellar objects. Not 3I. Atlas is moving too fast and we don't have the hardware ready, but a future visitor detected years in advance could, in theory, be reached by a swift spacecraft in 2019. The Initiative for Interstellar Studies outlined a mission concept called Project Lyra, using gravitational assist from Jupiter to accelerate a probe fast enough to chase Oumuamua. Their math suggested it was just barely possible with current propulsion, though it would demand a decade-long flight. The idea isn't as crazy as it sounds. If we detect an interstellar object 5 or 10 years before it reaches perihelion, the closest point to the sun, we could potentially launch a spacecraft to rendezvous with it, either on the way in or on the way out. A probe equipped with cameras, spectrometers, and maybe even a small sample return capsule could give us data telescopes can't. You could map the surface in fine detail, estimate the density by watching how the spacecraft's trajectory is tugged by the object's gravity, maybe even attempt a careful touch-and-go landing, if conditions allow, for a few heartbeats of orbital time. The engineering challenges are immense. Matching velocities with something moving at 30+ kilometers per second is no joke, but it's technically within the realm of physics. And the scientific payoff would be extraordinary. NASA and ESA have both commissioned studies on rapid response missions to interstellar objects. Nothing is funded yet, but the blueprints, at least, exist. Now let's talk about the public reaction. Every time an interstellar object is discovered, a wave of coverage rolls in. Some of it is careful and accurate. A lot of it is loud and sensational. Headlines shout about mysterious alien visitors and objects defying physics. Social media lights up with speculation. And inevitably someone says it's an alien spacecraft. Here's the thing. It almost certainly isn't. The Oumuamua alien hypothesis drew attention because Avi Loeb is a prominent scientist and he made serious arguments for why it couldn't be dismissed outright. But the vast majority of astronomers remain unconvinced. Extraordinary claims require extraordinary evidence. And we can't fully explain the acceleration is not the same as therefore. Aliens, still. The public fascination can be useful. It pulls people into astronomy. It makes them ask questions. And if that curiosity turns into support for better funding for detection systems and planetary defense, then honestly, some of the speculation ends up serving a purpose. What we need is science literacy, helping people understand what we know, what we don't know, and how we figure things out step by step. 3i, Atlas, is a perfect teaching moment. It's real, it's happening, and it's reachable, in the sense that anyone with a decent telescope might observe it during the flyby. Schools can host viewing nights, universities can hold public talks. It's an opportunity to spark the next generation of scientists and space enthusiasts. And that brings us to the bigger picture. Because beyond the specific story of 3i, Atlas beyond the data, the surveys, the budgets, there's a philosophical question worth sitting with. What does it mean to live in a universe where objects from other star systems can visit us? For most of human history, we imagine our solar system as isolated. The sun, the planets, the asteroids, the comets, everything was ours. Born here, staying here. A closed system turning through the dark, as if the cosmos itself had shut the gates. We knew other stars existed. Of course, but they felt so impossibly far away that they might as well have belonged to another universe. There was our stuff, and there was everything else, and never the two would meet. Oumuamua shattered that illusion in 2017. Suddenly the universe wasn't separate anymore. A piece of another star system crossed the unimaginable distance between suns and slipped through our neighborhood. And now, with 2i, Borisov, and 3i, Atlas, we're realizing this isn't rare. It's normal. The galaxy is interconnected. Matter drifts and trades between star systems. We're not isolated. We never were. Think about what that means in human terms. Every previous generation looked up and saw unreachable points of light. But you, right now, are living in the era when we've confirmed that pieces of those distant systems can reach us. You're witnessing the moment when humanity's neighborhood expanded from one star to potentially billions. And here's the profound part. These interstellar objects are ancient beyond comprehension. 3i, Atlas could be older than Earth itself. It might have formed 5 billion years ago, around a star that has since swollen into a red giant, or died in a supernova. This chunk of ice and rock could be a fossil from a planetary system that no longer exists, carrying chemical fingerprints from a world that vanished long before humans ever walked the Earth. When you look at 3i, Atlas, or even just the data it gives us, you're looking at deep time made tangible. Carl Sagan used to say, "We're made of star stuff." And he was right. The atoms in your body were forged in stellar furnaces billions of years ago. But now we know something even more humbling. Star stuff from other stars passes through our solar system. Quietly. Now and then. The iron in 3i, Atlas might have been created in a supernova, entirely unrelated to the one that seeded our solar system. This isn't only cosmic recycling within one star's family. It's material exchange across the entire galaxy, slow, steady, and endlessly patient. That has implications for the origin of life that scientists are only beginning to grapple with panspermia. The idea that life, or at least its building blocks, can be transferred between star systems used to sound fringe. But now we know interstellar objects pass through regularly. We know some carry organic molecules. And we know microorganisms can survive in space under the right conditions. Could life on Earth have been seeded by an interstellar comet that crashed here billions of years ago? It's still speculative, but it's not impossible. Even if panspermia isn't how life began here, the principle remains: we may be part of a galactic ecosystem. The boundaries between star systems are more porous than we once believed. What happens around one star can, over vast timescales, affect what happens around another. The universe is more connected than we ever imagined. But let's bring this back to December 19th, 2025, and what it means for you, personally. Here's what I want you to carry with you. We're living in a pivotal moment, the first generation that can detect interstellar visitors. The first generation with the tools to potentially defend our planet from cosmic impacts. And the first generation that can realistically dream about sending our own probes to intercept objects from other star systems. Our ancestors looked up and saw gods. Omens, navigation marks. We look up and see physics in motion gravity wells. Orbital mechanics, the evidence of planet formation. But both perspectives share one thing: wonder. And 3i, Atlas should awaken that wonder, because it represents everything we've learned and everything we still don't know. On December 19th, when this object makes its closest approach, take a quiet moment to picture what's happening. A visitor from another star, traveling for potentially millions of years through the cold darkness. is passing by our planet. It has been alone beyond imagining out there in interstellar space. No sunlight, no warmth, just cosmic radiation and the occasional wandering hydrogen atom. And for a brief moment, it's here close enough that we can study it and learn from it before it slips away again. Likely forever. The scientists watching will gather data that helps us understand not just this one object, but planetary formation across the galaxy. They'll be testing detection systems that might one day save humanity from a real impact. They'll be laying groundwork for missions that could, decades from now, meet an interstellar object up close. This is science in real time messy, uncertain, collaborative, and absolutely essential, done with steady hands and sleepless focus. But beyond the science, there's something deeply human in it. We're curious creatures. We face the unknown, and we want to understand it. We see a mystery, and we build telescopes to meet it. 3I. Atlas is a reminder that the universe is full of questions waiting to be explored, and sometimes, if we're patient and paying attention, those questions drift right to our doorstep. So what happens after December 19th? We keep watching. We keep learning. We keep building better detection systems, faster spacecraft, and more sensitive instruments because 3I, Atlas isn't the last interstellar visitor. It's simply the latest. There will be more, maybe dozens more in our lifetimes. If the LSST delivers on its promise, maybe one will be so strange it forces us to rewrite pieces of planetary science. Maybe one will arrive on a trajectory that's a little too close for comfort, and we'll finally have to use planetary defense systems for real. Or maybe, and this is the hope, we'll just keep adding data points, building our catalog of interstellar objects, learning about the galaxy one quiet wonder at a time. We'll trace some back to their home stars. We'll intercept one with a spacecraft and bring back samples. We'll unravel the mysteries that Oumuamua and 3I, Atlas posed, slowly, patiently, piece by piece. And we'll understand our place in the galaxy, not as isolated inhabitants of one star system, but as participants in a cosmic community, exchanging matter and energy for billions of years. December 19th, 2025 is just one day, but it's a day when you'll truly know that we're not alone in the universe. Not because aliens are visiting, but because the universe itself is visiting, bringing pieces of distant worlds to our doorstep. And if you look up that night, even if you can't see 3I, Atlas with your naked eyes, you can know it's up there, racing past at impossible speed. A messenger from the deep, carrying stories written in chemistry and physics. We're living in the age of interstellar visitors. We're living in the age when humanity learned to defend its home planet from cosmic threats. We're living in the age when the universe stopped being something we only observe and started being something we can, in small ways, interact with. That's worth celebrating. That's worth funding. And it's worth remembering when the next mysterious object appears in our telescopes, because it absolutely will. The galaxy is vast. The distances are incomprehensible. But every so often, something crosses that gulf and reminds us we're part of something bigger. 3I, Atlas, is that reminder. Pay attention to it. Learn from it. And when it's gone, keep looking up. Because the next visitor is already, quietly, on its way, already moving, already drifting, already real. Patterns in size distribution are most of them tiny, fleeting specks. Or is there a hidden population of larger bodies we simply haven't caught yet? Patterns in trajectory. Do they arrive from every direction at random? Or do we see subtle clustering that hints at shared origins? And here's the thrilling part: with enough detections, we may be able to trace some of them back to specific star systems, following breadcrumbs that fade, but don't vanish, into the dark. Right now, we can't say with certainty which star 3I, Atlas came from, because the uncertainties in its path grow dramatically when you rewind millions of years. But if we spot an interstellar object early, track it with exquisite precision through its entire passage, and it happens to be relatively young, maybe only a few 100,000 years into its journey, we might actually pinpoint its origin star. Just imagine that. Imagine being able to say, calmly and clearly, this object came from Tau Ceti, or this comet was ejected from the planetary system around Epsilon Eridani. Names we've only whispered in textbooks and late-night lectures. Suddenly you're not studying a random rock. You're studying a physical sample from a specific star you can point a telescope toward and observe. You could compare the object's chemistry to that star's spectrum and learn what planet formation looked like in that exact neighborhood. Some researchers are even proposing missions to intercept interstellar objects. Not 3. Atlas is moving too fast and we don't have the hardware ready. But a future visitor detected years in advance could, in theory, be reached by a swift spacecraft. In 2019, the Initiative for Interstellar Studies outlined a mission concept called Project Lyra, using gravitational assist from Jupiter to accelerate a probe fast enough to chase Oumuamua. Their math suggested it was just barely possible with current propulsion, though it would demand a decade-long flight. The idea isn't as crazy as it sounds. If we detect an interstellar object 5 or 10 years before it reaches perihelion, the closest point to the sun, we could potentially launch a spacecraft to rendezvous with it, either on the way in or on the way out. A probe equipped with cameras, spectrometers, and maybe even a small sample return capsule could give us data telescopes can't. You could map the surface in fine detail, estimate the density by watching how the spacecraft's trajectory is tugged by the object's gravity, maybe even attempt a careful touch-and-go landing, if conditions allow, for a few heartbeats of orbital time. The engineering challenges are immense. Matching velocities with something moving at 30 plus kilometers per second is no joke, but it's technically within the realm of physics, and the scientific payoff would be extraordinary. NASA and ESA have both commissioned studies on rapid response missions to interstellar objects. Nothing is funded yet, but the blueprints, at least, exist. Now let's talk about the public reaction. Every time an interstellar object is discovered, a wave of coverage rolls in. Some of it is careful and accurate. A lot of it is loud and sensational. Headlines shout about mysterious alien visitors and objects defying physics. Social media lights up with speculation. And inevitably someone says it's an alien spacecraft. Here's the thing. It almost certainly isn't. The Oumuamua alien hypothesis drew attention because Avi Loeb is a prominent scientist and he made serious arguments for why it couldn't be dismissed outright. But the vast majority of astronomers remain unconvinced. Extraordinary claims require extraordinary evidence. And we can't fully explain the acceleration is not the same as therefore. Aliens, still, the public fascination can be useful. It pulls people into astronomy. It makes them ask questions. And if that curiosity turns into support for better funding for detection systems and planetary defense, then honestly, some of the speculation ends up serving a purpose. What we need is science literacy, helping people understand what we know, what we don't know, and how we figure things out step by step. 3i. Atlas is a perfect teaching moment. It's real, it's happening, and it's reachable, in the sense that anyone with a decent telescope might observe it during the flyby. Schools can host viewing nights. Universities can hold public talks. It's an opportunity to spark the next generation of scientists and space enthusiasts. And that brings us to the bigger picture. Because beyond the specific story of 3i, Atlas, beyond the data, the surveys, the budgets, there's a philosophical question worth sitting with. What does it mean to live in a universe where objects from other star systems can visit us for most of human history? We imagined our solar system as isolated. The sun, the planets, the asteroids, the comets, everything was ours. Born here, staying here, a closed system turning through the dark, as if the cosmos itself had shut the gates. We knew other stars existed, of course, but they felt so impossibly far away that they might as well have belonged to another universe. There was our stuff, and there was everything else, and never the two would meet. Oumuamua shattered that illusion in 2017. Suddenly, the universe wasn't separate anymore. A piece of another star system crossed the unimaginable distance between suns and slipped through our neighborhood. And now, with 2i, Borisov, and 3i, Atlas, we're realizing this isn't rare. It's normal. The galaxy is interconnected. Matter drifts and trays between star systems. We're not isolated. We never were. Think about what that means in human terms. Every previous generation looked up and saw unreachable points of light. But you, right now, are living in the era when we've confirmed that pieces of those distant systems can reach us. You're witnessing the moment when humanity's neighborhood expanded from one star to potentially billions. And here's the profound part, these interstellar objects are ancient beyond comprehension. 3i. Atlas could be older than Earth itself. It might have formed 5 billion years ago around a star that has since swollen into a red giant or died in a supernova. This chunk of ice and rock could be a fossil from a planetary system that no longer exists, carrying chemical fingerprints from a world that vanished long before humans ever walked the Earth. When you look at 3I, Atlas, or even just the data it gives us, you're looking at deep time made tangible. Carl Sagan used to say we're made of star stuff. And he was right. The atoms in your body were forged in stellar furnaces billions of years ago. But now we know something even more humbling. Star stuff from other stars passes through our solar system. Quietly. Now and then. The iron in 3I, Atlas might have been created in a supernova entirely, unrelated to the one that seeded our solar system. This isn't only cosmic recycling within one star's family. It's material exchange across the entire galaxy. Slow, steady, and endlessly patient. That has implications for the origin of life that scientists are only beginning to grapple with panspermia. The idea that life, or at least its building blocks, can be transferred between star systems used to sound fringe. But now we know interstellar objects pass through regularly. We know some carry organic molecules. And we know microorganisms can survive in space under the right conditions. Could life on Earth have been seeded by an interstellar comet that crashed here billions of years ago? It's still speculative, but it's not impossible. Even if panspermia isn't how life began here, the principle remains we may be part of a galactic ecosystem. The boundaries between star systems are more porous than we once believed. What happens around one star can, over vast timescales, affect what happens around another. The universe is more connected than we ever imagined. But let's bring this back to December 19th, 2025, and what it means for you. Personally, here's what I want you to carry with you. We're living in a pivotal moment, the first generation that can detect interstellar visitors, the first generation with the tools to potentially defend our planet from cosmic impacts, and the first generation that can realistically dream about sending our own probes to intercept objects from other star systems. Our ancestors looked up and saw gods. Omens. Navigation marks. We look up and see physics and motion gravity wells. Orbital mechanics. The evidence of planet formation. But both perspectives share one thing: wonder. In 3I, Atlas should awaken that wonder, because it represents everything we've learned and everything we still don't know. On December 18th, when this object makes its closest approach, take a quiet moment to picture what's happening. A visitor from another star, traveling for potentially millions of years through the cold darkness, is passing by our planet. It has been alone beyond imagining out there in interstellar space. No sunlight, no warmth, just cosmic radiation and the occasional wandering hydrogen atom. And for a brief moment, it's here close enough that we can study it and learn from it before it slips away again. Likely forever. The scientists watching will gather data that helps us understand not just this one object, but planetary formation across the galaxy. They'll be testing detection systems that might one day save humanity from a real impact. They'll be laying groundwork for missions that could, decades from now, meet an interstellar object up close. This is science in real time, messy, uncertain, collaborative, and absolutely essential, done with steady hands and sleepless focus. But beyond the science, there's something deeply human in it. We're curious creatures. We face the unknown and we want to understand it. We see a mystery and we build telescopes to meet it. 3I. Atlas is a reminder that the universe is full of questions waiting to be explored, and sometimes, if we're patient and paying attention, those questions drift right to our doorstep. So what happens after December 19th? We keep watching. We keep learning. We keep building better detection systems, faster spacecraft, and more sensitive instruments, because 3I, Atlas isn't the last interstellar visitor. It's simply the latest. There will be more, maybe dozens more in our lifetimes. If the LSST delivers on its promise, maybe one will be so strange it forces us to rewrite pieces of planetary science. Maybe one will arrive on a trajectory that's a little too close for comfort, and we'll finally have to use planetary defense systems for real. Or maybe, and this is the hope, we'll just keep adding data points, building our catalog of interstellar objects, learning about the galaxy one quiet wanderer at a time. We'll trace them back to their home stars. We'll intercept one with a spacecraft and bring back samples. We'll unravel the mysteries that Oumuamua and 3I, Atlas possess, slowly, patiently, piece by piece, and we'll understand our place in the galaxy, not as isolated inhabitants of one star system, but as participants in a cosmic community, exchanging matter and energy for billions of years. December 19th, 2025 is just one day, but it's a day when you'll know, truly know that we're not alone in the universe. Not because aliens are visiting, but because the universe itself is visiting, bringing pieces of distant worlds to our doorstep. And if you look up that night, even if you can't see 3i, Atlas with your naked eyes, you can know it's up there, racing past that impossible speed. A messenger from the deep, carrying stories written in chemistry and physics. We're living in the age of interstellar visitors. We're living in the age when humanity learned to defend its home planet from cosmic threats. We're living in the age when the universe stopped being something we only observe and started being something we can, in small ways, interact with. That's worth celebrating. That's worth funding. And it's worth remembering when the next mysterious object appears in our telescopes, because it absolutely will. The galaxy is vast. The distances are incomprehensible. But every so often, something crosses that gulf and reminds us we're part of something bigger. 3i, Atlas is that reminder. Pay attention to it. Learn from it. And when it's gone, keep looking up. Because our next visitor is already, quietly, on its way, already moving, already drifting, already real.